All right, guys, in this video, we're going to look at the rates of decay and half-life equation. So let me get my tablet working here, pull up my pen. All right, so before we really get into radionuclides and decay, we've got to talk about what a logarithm is. And hopefully, if you're taking chemistry, you should either be done with or in Algebra 2. You'll see some logarithms in Algebra 2, but in case you haven't got there yet, or if you need a refresher, this slide is like everything about logarithms you need for like basic understanding. So, what is a logarithm? A logarithm is a different way to write an exponential relationship, okay? Normally, if we said, hey, what's 2 to the 4th power? Well, 2 to the 4th is 16. So I've color-coded these specific numbers for a reason, okay? Another question we could ask is, 2 raised to what power is 16? Well, the answer is 4. We know that because, obviously, I've just restated this problem up here. But I can express that with a logarithmic equation. The log base 2 of 16 equals 4. That's what this says. Log base 2 of 16 equals 4. Well, are these two things the same thing then? Well, the answer is actually yes. All right, they are the exact same thing. They're just demonstrating two different facts. Number one, exponential form, which is this, exponential, it isolates the power, okay? This is logarithmic. Logarithmic. You remember how to spell it there for a second. The logarithmic form, all right, is going to isolate the exponent. Logs are useful ways to find exponents, okay? That's what a logarithm does. It allows you to solve for an exponent. And this 2, right, these color-coded 2s, if you know the outcome and you know the number you want to start with, then you can solve for the exponent, all right? Now in your calculator, you have a log button. It's on the left-hand side of the calculator. It looks like this, log. And it is naturally, when you punch it in, it is log base 10. Anytime you don't see a base, you can assume it's base 10. That's the log that we're going to use. So let's talk about half-life. And you'll understand very quickly why I'm talking about half-life, or sorry, why I'm talking about logarithms. And that's because a logarithm graph and a half-life curve look eerily similar. Basically, the decay of a radioactive substance, if you map out the amount of radioactivity, or radioactive substance rather, against time, it will form this graph right here pretty much every time. Now, the thing that will change is the length of time it takes for things to decay, but the overall shape of the graph is logarithmic in nature. It looks just like that. And what we're seeing here is half-life in action. So if I have a 100-gram sample, after one half-life, I should be left with 50 grams because half-life is the amount of time it takes for half of an original sample to decay. So I can see that here is my original sample. There's my original sample. And after one half-life, there we are, after one half-life at 50. And that makes sense. After two half-lives, well, divided by 2 again, I should be at 25 grams. Well, there we are, 25 grams. There's 2 half-lives. After 3 half-lives, well, 25 divided by 2, it's going to be 12.5 grams. And we look, and sure enough, it's just above halfway. That makes sense. There's 3 half-lives. 12.5 divided by 2 is 6.25 grams. And so on and so forth, all the way down. Now, in this case, it looks like the half-life is, well, it doesn't give us a unit, does it? So that's not a very good graph. There is a corresponding graph that goes with it called the daughter curve, and it is equal and opposite to the parent curve. Now, I wonder why we might need a daughter curve. Well, let's think way back to some of our nuclear reactions. Let's say we take, I don't know, let's do carbon-14. That's an easy one. Carbon-14, and we're going to say it's going to break down by alpha decay, just as an example. Well, then I'm going to make 4, all right, 10 on top, and number 4, I believe, is beryllium. Is that right? Yes, beryllium, I hope, since I'm making a video. I don't have my periodic table in front of me, so I'm guessing. So whatever element number 4 is, I think it's beryllium. That's going to be the product. So this is the daughter species in this reaction. This would be the parent species. Here's another one for you, right? Uranium 235, 92. It breaks down by 4,2 helium for alpha decay, and it's actually going to form number 90 and 231. This is thorium. All right, again, this is the daughter, and this is the parent. So as the parent breaks down, right, the parent is breaking down, the amount of the daughter is correspondingly increasing. This is a really useful thing to know if you want to date something, if you want to age something. So if I know, hey, I've got this much daughter and I've got, X amount of parent, I can work back, figure out how long ago it is, and this distance right here would be the age of whatever sample I've got, right? So pretty useful thing as far as radiocarbon dating and stuff like that. Now, the half-life equation for simple problems is literally just divide by 2. So if I'm working a simple problem and it says something like, I've got a 100-gram sample, how much is left after 3 half-lives? Well, okay, divide by 2, divide by 2, divide by 2. Well, that's going to give me 50, 25, 12.5. Hey, I got 12.5 grams left. Simple stuff, okay? We are, however, in Chem Honors, and so we're going to see a little bit more complicated set of problems, and I'm going to show you the integrated rate equation. So this is the integrated rate equation. Now, you want to know these variables down here, right? We want to know these. If you don't know these, if you can't pull them out of the word problem, then you can't solve the equation. But basically, the log of the amount of sample present at the beginning divided by the amount of sample that you currently have at some time t is equal to sometime t multiplied by k, which is the rate constant. This is different for every single element. It will either be given or you'll calculate it, divided by 2.303. And that will let you solve, that is the integrated rate equation. You can also, depending on the problem, use N0 over N, where N is relative activity and N0 is the original activity. And we'll see one of those in a minute. You also need to know how to find half-life. Now, notice this is the same K as we used a minute ago. So when we're talking about our other equation, this K right here is that K right there, same number. So I can find K if the problem gives me half-life using that equation right there, or I can find half-life if I know K. Half-life is equal to the ln of 2 over 3. Now, there is a natural log button on your calculator. That's what ln means. ln equals natural log. I think it might even be second log. I don't have my calculator right here, but I think it's second logarithm. But if not, it's an ln button. Okay, depends on the calculator you have. So let's see one of these in action. All right, cobalt-60 decays with the emission of beta particles and gamma rays with a half-life of 5.27 years. How much of a 3.42 microgram sample of cobalt-60 remains after 30.0 years? All right, well, the first thing I need is I need to find k. I know I need k because I need to use my integrated rate equation. I know that k is the natural log of 2 divided by the half-life, and it gives me the half-life right here. So I'm going to do that first. Now, notice something about this unit right here. This is year to the negative 1. Now, I'm going to do a little sidebar over here and talk about exponents for a minute. If you have 1 over x, that is equal to x to the negative 1. If you have negative 1 as a power, what that means is put something into the denominator. All right? I know that doesn't look like denominator, but I ran out of room. So when I see 0.693 divided by 5.27 years, well, there is no unit up here. All right, that's just a number. So there's nothing for me to cancel out years. So really the answer I get is this, 0.1315 divided by years. But that doesn't really look good. So we move year up to the top, and we give it a negative 1 exponent to show that it goes on the bottom. That negative 1 exponent is going to be really important because if I multiply x to the negative 1 times x, well, when you multiply exponents, we know that we add them. And if there's no exponent, there's a 1. Negative 1 plus 1 is 0. That's going to give me x to the 0. Well, anything to the 0 power is 1. And anything times 1 is itself. So if you can multiply a negative 1 exponent times a regular 1 exponent, it cancels out. And that's what we're actually going to see. So that's the skinny behind that negative 1 right there. The second thing I need to do is I need to use my integrated rate equation. And literally all I'm doing is plugging in variables from the problem. It looks complicated, but it's really not. So let's go through the problem and see if we can figure this stuff out. So A sub 0 is the amount of starting material. Well, it says how much of a 3.42 microgram sample of cobalt will remain after 30 years. So this is what I'm starting with. So since I'm starting with that, it's A sub 0. The amount when time equals 0 is what that means. I don't know A because it's how much remains. So how much remains? T is 30 years. There's T right there, my 30 years. And I know K, right, because I just found it. And this is a part of the equation. So I've plugged everything in. So now I just need to solve for A. So we simplify. So we multiply the top, divide by the bottom here. Notice year negative 1 times years cancels out. All right, so I have no unit left on the right, which is a good thing. Okay, I'm trying to find how much of this microgram sample remains. So I should get an answer in micrograms. So I'm going to need to cancel out years at some point. And fortunately, I have micrograms left. It's the only unit left in the problem, so I know I'm on the right track. But here's the question. What kind of algebra do I do to solve for A? How do I get rid of the log? It's actually really easy. Remember I said a minute ago that if you see log and there's nothing next to it, it's base 10. Well, if you raise 10 to the log base 10 of something, they cancel, and you just have, let's say it's x, you just are left with x. So take the antilog, 10 to the x, of both sides. So when I take my antilog of both sides, what I'm doing is I'm raising both sides as a power of 10. So 10 to the log of 3.42 micrograms over A equals 10 to the 1.713. That's what I've done. And you can see that here on the right. Well, the thing about this is that's going to cancel. All right, we're going to get rid of that. And so I'm left with 3.42 micrograms over A equals 10 to the 1.713. And now, once we've gotten this far, we are just back in the realm of regular algebra. We're going to multiply A to both sides. We're going to simplify 10 to the 1.713. We're going to divide, and we're going to find that A is 0.0662 micrograms. This step right here is the only new step that we're really talking about. Once you get your logarithm simplified as much as you can, to get rid of the logarithm, just set both sides as a power of 10. Now, what do we use this for? Well, the big thing is aging a specimen, all right? And if they're organic, we can use carbon-14 to date them. So let's look at one of those. And this is an equation where we'll use the N0 instead of the A0. So it says a piece of wood is taken from a cave dwelling in New Mexico and found to have a carbon-14 activity per gram of carbon, only 0.636 times that of wood today. Here's the dead giveaway that you're using N, not A. It says activity. Estimate the age of the wood, and the half-life of carbon-14 is 5730 years. Well, same as last time. I'm only going to use my integrated rate equation. I need to find K. The problem gave me half-life, so I'm going to plug that into the K equation. There's my K right there. I have year -1. Now, because it says activity per year today, I'm going to use N0 and N, not A0 and A. N is equal to 0.636 N0. So how do I know that? All right, well, this is a math reading skill. It says the activity is 0.636 times that of wood. Whoa, go back. Sorry. Here we go. So let me restart that thought. So how can I figure this out right here? Okay. I know it says that the activity that it's found to have is 0.636 times that of wood today. Well, N is the activity now, and N sub 0 is activity when time was equal to 0 at the beginning, at the start of the sample's existence. So since it's 0.636 times that of wood today, I'm just going to multiply the original times 0.636. Now I can get rid of N. I can substitute N with N sub 0. I'm going to plug that in. N equals 0.636 N0, so that's what I plug in for N. Now notice something. I have N sub 0 divided by N sub 0, so that's going to cancel. I'm looking for the time, right, because I want to figure out how old it is. Well, so this is just going to cancel. That's going to leave me with 1 over the top. This I can just put into my calculator. Log of 1 over 0.636. It will give me a number. That number is 0.19654. Then I'm going to divide both sides, right? I'm just back in algebra land, and it tells me that roughly this sample is 3,740 years old. Now, radiocarbon dating is pretty cool, but anything older than about 50,000 years, there's not enough activity left to date accurately with carbon dating, so we use potassium-40 or use uranium-238 dating. Potassium-40 has a half-life of like 1.3 times 10 to the 9th years, so it's a lot of years, right? 3, 6, 9, right there, years. So hundreds, thousands, millions, billions. So that's 1.3 billion years. So that's really good for dating rocks. And uranium lead dating is actually even more accurate, even more longer lived, right? It's 4.51 billion years is a half-life. So when we date like the moon rocks or rocks that you find in like the interior of a continent, we usually use potassium argon or uranium lead dating. It was uranium lead dating right here that was actually used to date the age of the Earth, which is interesting. So let's do one of those. A sample of uranium ore is found to contain 4.64 milligrams of uranium-238 and 1.22 milligrams of lead-206. Estimate the age of the ore. All right, well, I need to convert the ratio of uranium that's there now lead that's there now back into the uranium I started with. So I'm going to use their molar masses to do that ratio. And I'm going to get 1.41 milligrams of uranium that has disappeared. Now, this is not a question I'm going to ask you to do on a test. This is just more for enrichment activity, but that is how I would do that. I would look at the ratio of their two masses, and that would allow me to get back over to how much uranium is gone. I know that 1.41 milligrams of uranium has decayed. I know that I currently have 4.64 milligrams left, so added up, it tells me A sub 0, the amount of uranium at the beginning when time equals 0. This is what I started with. And if I know what I started with, well, I can find K in my inverse years. I know A sub 0, so I'm going to plug those numbers in. The only thing I don't know is T, and now I'm just solving T. So this would be a 1.73 billion year old ore. It's pretty interesting. Here's another one, strontium. Okay, it says strontium 90 decays with the emission of beta particles with a half-life of 28.9 years. If 2.511 grams remains after 80 years, what is the mass of the sample? So you want to find K, use your half-life equation, solve the right side, take the analog of both, solve for A sub 0 and simplify. You should get 17 grams when you do this. So take a couple minutes, leave this screen up, and see if you get that answer right there. Okay? That's the original sample amount when time equals 0. Here's another one for you to do. Argon-42 decays by beta particles, has a half-life of 32.9 years. If you have 4.785 grams remaining of an 8.45 gram sample, estimate the age of the sample. So hopefully by now you know, hey, I'm looking for time, I'm looking for T. So I need to start the same way I always do. Find K, all right? Simplify the left side, solve for T, all right? Give it a couple minutes, try it. You should get 27 years. If you can do those two problems, then you are in good shape with the half-life equation. If you have questions, let me know. All right, and I'll be glad to give you a hand.